everyone, welcome to our channel. This is the first session on pyRosetta series and we're going to talk about pose. I assume that you already have installed pyRosetta on your Google Drive and you already know what pyRosetta is. So let's jump into it. First of all, by definition, pose is defined as a molecular system. So a pose can be a protein, it can be a small molecule, it can be a DNA, any kind of molecular system can be saved into a pose. When you think about a molecular system or you think about like a protein, you see that where each atom is positioned, kind of atom pose holds data about atoms or residues, coordinates of each atom and how they're connected to each other, or if there's an interaction between them like a disulfide bond. Also has information about energies or scores, which we will talk about in a session about the score function. From programming perspective, a pose is a class. And I'm going to just quickly talk about classes if you're not familiar with them. Classes in C++ or any other language can be looked as some object holders. So imagine you have a bank account and you have a card and your information is written on this card, like your card number, expiration date, your name, so on. So this card is specific to you, but the bank that makes these cards has a bunch of cards without any number on them, and then it prints out the specific numbers for each user, right? And those cards, like those general cards, are kind of equal to classes. So we have some general classes defined, like a general card, and then you can specify information to it and it becomes an object. Same is for pose. So pose is a class in general and your biomolecule is an object which is can be a specific protein or DNA. As you can see, when you look at the card, there's a place for holder's name, for card number, for expiration date, for your password. Each of those placeholders for the information are called attributes. Also, your card has some function, so you can pay with it. It can be used for identification, and those functions are also like hard-coded inside the card, and those are called methods. So each class can have some functionality as well, and those functionalities are called methods. Header file for pose is in this path. Now let's start coding. I'm going to code in Colab environment. First of all, you should have a folder in your Google Drive which has all Rosetta files inside it, and I assume you have it. If not, you can let me know and I can make a video about it, but that's just easy and straightforward and you can do it by yourself, I think. First of all, you need to connect Colab to Rosetta. So you pip install the pyRosetta Colab setup. Let's run it. Then you just import that library, and then you mount pyRosetta install, which here it connects to your Google Drive, and you should allow access to it. I have done it before, so it doesn't ask me another time. But when you run it, it asks for access to your Google Drive, and it might also ask for user and password. Which should be emailed to you if you're a part of Rosetta Commons. Now we should I start with a general approach, and from pyRosetta I import everything, and don't forget to initialize it. This is very important. Great. Now it's time to start working with a pose. You can get a pose from different ways. The easiest way, I think, is getting pose from rcsb or pdb, and then here I write the ID of that pdb file, and then I save the information of this pose into my object and I call it my pose object. Let's do it. And you can see that there are some warnings, but at this stage, you don't need to worry about any of the things. So I just, okay, let it be. Next, we can do a bunch of stuff up on pose, but I'm talking in this session about some basic things that can be, the result can be printed out very easily. First of all, you can see how many residues you have in a pose. So you say the name of your pose, the name of your object, which is my pose object, the total residue, and it reports the number of residues in your pose. Before going further, I also want to show you, so here I imported this file, and then if I look at the files here, I see that there are two files named 7x2j.cleanpdb and then a pdb file. I open them in text format, and then I show you the difference between these two files. Okay, here I have, on the left, I have the pdb file, and on the right, I have the clean pdb file. As you can see, the pdb file has a bunch of headers and some explanation and information before going to the information about atoms and their coordinates. In clean PDB, we don't have any of this information. So all this information is removed, and we only have information about atoms and their coordinates. Also, if I go to the end of this clean PDB file, you see that here the last one is number 2596, which is the number of atoms. But if I go to the end of this file, beside that, we don't have this connection. The last atom here is 2675, which is more than this. So what has happened? You can see that this is a heteroatom, which means it belongs to a non-canonical amino acid or some heteroatom, whatever. And when you look at the name of this atom, these are from water. So this is HOH type. So O, not only water, but any type of solvent is removed in clean.pdb. Also, if I go a little up, here you can see that like 2596 is here, which is assigned as TR or terminal or termination of the protein. And after that, we have another thing called NAG. NAG is just a small molecule. It is ligand to this protein. And so in clean PDB, the ligands are also removed, and we only have information about our protein. I can say this is the minimum adequate information that you can reconstruct your molecule with it. And if I open this with PyMol, it can show the molecule properly, and everything in PyMol that you can do on that on an original PDB file can be done on clean PDB file as well. So let's look at it very quickly. This is clean PDB file, and this is just the same molecule. Okay, now going back to our pose here. So you could get total number of residues in your pose, which is 323. Another way to get the number of residues is using .size. So if let me write it again. If I say my pose object.size, I get the same results. And I recommend to use .size instead of total residue. You can also get the number of atoms. I'll remove this. Okay, number of atoms can be shown with total atoms. So again, your pose and then the total atoms. We have 4994 atoms in this pose. By .empty, you can check if your pose has some info in it or it's empty. So because you can just declare a pose, initiate it without assigning any pose to it, and we will talk about it later. But here you can check if it's empty or not, and it returns false. It means we have something inside our pose, inside our object. Next thing is number of jumps. So when you have a string of amino acids or residues, there might come from different chains. So it doesn't mean that we have peptide bind between each two amino acid. In places that two residues are not connected to each other, it means that we have, for example, two chains, there is a jump. And this function shows the number of jumps in this pose. And when I run it, I get 1. So think for a moment, if I have 1 jump, it implies that how many chains do I have? 2, right? Because if I have 2 chains, there is some break in between. And now I can, let me print the number of chains. And then it gets me 2. So I have 2 chains and there is 1 jump between them. Next, I can also get type of amino acid. This is one kind of lame way because it, let me just show you. So you get, your pose object.aa and then the number of the position of that residue. And also here, I should say that the position of residues start from 1 in Rosetta, not from 0. So 3 means I want to see which amino acid is the 3rd residue, and it shows me that it is cysteine. But if, as you can see, this returns an object. It's not a string, so it's not a good way. But we can use this in other applications. Then I can also get the secondary structure of a residue. So let me get the secondary structure of 3rd residue, and it returns L, which stands for loop. It might return H for helix and E for beta sheets. Okay, I can also get this secondary structure of the whole pose as a string, not just a single residue. And for that, you should just use secstruct without any number. And here it returns a string, and you can see that all the residues are assigned as L. And this is because it doesn't really go to predict the secondary structure for you. And so this is wrong. But there are some pose files that you have the info about secondary structure in them, and you can get the true secondary structure. But here it's wrong, and not all residues here, as you saw in PyMo, they're not all loops. Also, you can change the type of secondary structure for residues, and you can say set secondary struct for residue number, let's say 3 to helix, and it does it. So if I get the secondary structure for the sequence another time, you can see that the 3rd one is changed from L to H. Yeah, but it doesn't change any coordinates or anything. This is just to change the type. So you can't just use it. It doesn't change the real structure. It's just some assignment. Next, you can get the sequence of your pose. So I just write my pose object.sequence, and you get the sequence by 1-lettered amino acids for residues. I can also get a sequence for part of protein, and for that you just write sequence same, but you enter a starting point and ending point for where you want. And I want first 10, so I get 1, 2, 10, and it returns the first 10 amino acids. And you can see this is the same as here, right? Next, you can also get annotated sequences. Let me run it and then I can explain. So by annotated sequence, you can see that. So for example, you get N-terminal protein, where the N-terminal is where you have disulfide bonds, and in the middle of protein, we have another N-terminal and C-terminal because we have 2 chains, right? If you have some non-canonicals or anything else that needs an explanation, those are annotated and you can get them in annotated sequences. Next, you can also get torsion angles, including phi and psi, for each residue. Let's just print it out, and it is reported in degrees. Just another point that I should say, you can see the phi angle for the first amino acid, first residue, and the psi angle for the last one, which was 323, are 0. But if you have a cyclic peptide, those phi and psi angles are computed with regard to some virtual atoms. And as a result, it reports a wrong angle. So just be careful about using this for the terminal parts if there is a cyclic molecule. And you can get other like chi, omega, theta, any other angles that are defined in other biomolecules. All of them are defined in Rosetta, and you should just change the name here. So I can write omega, and I get something, but I get theta, and I get an error because this is not defined here, right? Next, going to chain info. So we tried number of chains, and we got 2. You can get the sequence for each chain with entering the number of chain. So I can get the sequence for the first chain and sequence for the second chain. Yes. And you can also see what is the first residue of each sequence, each chain. And you can use chain begin. And I can get chain begin. Oh, sorry, this is the position, not the residue. This is the position. So the chain, I mean, this is obvious that this first chain begins with number 1, but I go with second one, and the second chain begins with number 197. So if I get the sequence for 197 up to, let's say, 200, this is QVQL, and this is the same as chain sequence for this one. And same as chain begin, I can also get the end of chain, the position for end of chain. So if I get chain end for number 1, it should be 1 less than this, right? It should return 196. And here it is. And if I get chain end for number 2, it should be the same as number of total residues or size, which is 323, right? You can also remove a pose from your object by setting your pose object.clear. And so it just did it and it finished, but you remembered from sometime earlier that we used .empty to check if a pose is empty or not, and it returned false then, but now we cleared the pose from this object, and the empty should return true if it works correctly. And you can see that it returns true. So to continue, I need to go up and run this line pose from rcsb another time. And now when I go down here, check if it's empty, it's false. I don't want to clear it another time, but you can do so. Next is dumping a pose. So you have a pose, and I mean, here we didn't change anything, but you can change some information in your pose, or you can create a pose, and now you want to save it in a file. So I have tried it earlier. Let's say very new 7x2j.pdb, and you write your pose.dump file and then name of your file, including the path with the right extension. You can use .pdb or .sif. Each of them work with file. Let's run it, and here when I check, I have very new .pdb here. We also have dump pdb and dump sif and dump escort pdb, but dump file is a general one, and dump escort pdb. We can also include scores, and we will use it later. I think it was all about pose, like some simple things that you can do and start coding. And here's a practice question. So I want you to write a code to report the percentage of systems in that have a disulfide bond in bovine serum albumin. And actually, I did something not wrong, but you see, because I had tried it before, and this is, I had imported it earlier, so you can see this is 4F, 5S for the PDB ID of BSA, and you can use it. But and I have another hint. So you can get the pose first, get the number of cysteines in sequence, get the number of disulfide bonds in annotated sequence, and then you can calculate the ratio. You can post your answers to this question in the comments or even your code, and I will talk about the answer of this question, which is pretty easy, but I will talk about it in the end of next video. So see you then, and let me know if you have any questions about this. Bye.